Hey folks, welcome to our next unit on thermodynamics, which is the physics of heat. As you can see, we have a handful of different topics that we're going to study throughout this unit. So we're going to go ahead and get started today by looking at temperature versus heat. So temperature is our way of measuring the kinetic energy of the particles in a system. And that's what's kind of unique about temperature, right? As we always associate, oh man, it's hot. Well, hot is relative, or oh, it's cold. Cold is relative. If we think about the grand scheme of temperatures that we can measure, yeah, 0 degrees Fahrenheit is cold. It's cold. We're not going to deny that, but it can get far colder than that. I mean, we see places on our planet where it's going to be negative 30 degrees Fahrenheit, negative 50, negative 80. You know, it gets really, really cold, right? Where suddenly, man, that 30-degree day feels really warm compared to something that's negative 100 degrees. And because of that, temperature is relative. Same thing where, 30 degrees feels real warm compared to negative 100. Well, 100 degrees feels a heck of a lot warmer than 30 degrees does. So we have three scales that we look at. Celsius, Kelvin are the two that we're going to primarily use here. We'll talk about things in Fahrenheit, but not directly use those in any calculations because everything is driven from Celsius and Kelvin. Recall that absolute zero is negative 273 degrees Celsius, which is negative 454 degrees Fahrenheit, right? That is really, really, really cold. And at that temperature, all atomic motion stops. So we've gotten really close to that in the lab. We've gotten really close to observing it, but we've never actually seen it. That's one of those thresholds that we have yet to be at and we have yet to see, but it's there. So one thing that's going to kind of help us look at temperature. As we see this graph here, we have the number of particles versus kinetic energy. This would balance out to giving us what our temperature is of a system. So here we see the kind of really light blue. We have, that 100K there. So we have a lot of particles at a low kinetic energy versus the 1000K, which is the red, where we don't have as many particles there, but they have more energy. So really, we need to average all of those kinetic energies to get what our temperature actually is. Because not every particle in the system is going to have the same kinetic energy, which means they're not all going to have the same velocity. It's about the overall system. What is the average of what's happening? So we're going to look at a quick simulation here. What we see are a bunch of circles that are various colors, and we can see in the bottom left here, we can look at, this is going to be our temperature, right? So we're going to get various energies here, and we're going to see an energy distribution where the blue scale is going to be the lower energy, the red is going to be in the middle, then orange, then yellow, then white is going to be the highest energy that we have. So if we reset this and then I play it, right, we can see the motion here. And as these particles collide with one another, we're going to see them transfer kinetic energy from one to the other. So depending on how they hit, we're going to see an increase in energy, we're going to see a decrease in energy, and we'd be able to find velocities based on conservation of momentum. We'd be able to figure velocities, and then we could see how much energy, kinetic energy, is gained by one object and lost by another through the collisions that occur. But we see this temperature stays pretty static based on the overall energy that's in the system. If I go up to the top and if I hit this heater, which is now going to introduce thermal energy to the system, now look at the amount of white particles and notice how the overall color scheme has shifted, right? So now we see a lot more white particles, more yellow particles, more orange, and we see fewer of the blue. So if you notice the curve in the bottom left here, it shifted to the right, which indicates this is at a higher temperature because the average kinetic energy of the particles has increased. Notice there are still some blue particles, there are still some purple, there are still some red. They're not all at the super high energy, but because more of them are, we're going to experience a higher temperature. Which then brings us to our next point, which is heat, right? And heat, as it says up here, we have two ways to define it, but ultimately, heat is a transfer of thermal energy, which is going to spontaneously occur from high temperature to low temperature. So because heat is an energy flow, right? It's an energy transfer. we are still going to measure heat in joules like we do all other forms of energy. So now this thermal energy measured in joules is going to show us how that energy spontaneously goes from high to low. And because it's going from high to low energy, it's going to go from high temperature to low temperature. We also look at this as our ability to do work, and in some cases it's going to be more of a potential energy, right? If one object has a high temperature, once you are allowing that energy to be released, that thermal energy can do work, and we just saw it in that simulation. We put the heater in there. That heater is going to increase the thermal energy of the system, right? And that thermal energy is then going to be distributed through contact by the particles that are in the system. Now, because it's the ability to do work and it spontaneously goes from high temp to low temp, that means in order for energy to flow from low to high, we actually need to do work in the system to make that happen. That is not a natural occurrence for it to go from low temperature to high temperature, right? It's always high to low. So in order for the low energy to transfer to the high energy, we need some external system to push that energy because it's not going to spontaneously occur that way. Think about if you have a glass, and if you drop the glass is going to shatter. That glass is not going to spontaneously pick itself up and piece itself back together. That takes work in order to go from that state of disorder to that state of order, which would be the glass itself. Now, we can look, what has more heat energy? We've got a hot tub here at about 102 degrees Fahrenheit and the entire Atlantic Ocean, which on average is about 50 degrees Fahrenheit. And depending on what you're looking at, your argument for the hot tub would be, well, it's hotter, which is true, but there's way more particles in the Atlantic Ocean. So if you were to dump that hot tub of water in the Atlantic Ocean, it's not going to make much of a difference, right? It's not going to do much work. If you were to take the volume of the hot tub and say it was 50 degrees Fahrenheit, then the hotter water would have more energy than the Atlantic Ocean water. But because we have so many more particles in the Atlantic Ocean is still going to have more heat energy available to do work simply based on the sheer volume that it has. So if you have equal masses of things, the higher temperature is going to have more heat energy. It's going to be able to do more work. If you have a difference in mass, then the hotter one could, if that temperature difference is able to overcome the mass difference. Which kind of brings us to our zeroth law of thermodynamics here. And this is the foundation of thermodynamics here. So we have three objects here. We have object A, B, and C. Clearly they are different sizes, and because of that, we're going to assume that they have different masses. So if A is the same temperature as B, and B is the same temperature as C, then by definition, A has to have the same temperature as C, right? Notice how they're all connected there. But just because it has equal temperatures does not mean that the energy values are going to be the same. Because they're all at equal temperature, the more massive object is going to contain more thermal energy because it is going to have more energy to give when work is going to occur. And if we look at the three masses here, A would have the least energy, C would have the middle amount, and B would have the most energy based on the fact that those are the order of their sizes from small to big, and they're all at the same temperature. And part of where we get that zeroth law comes from a piece of the second law of thermodynamics, which is going to be our heat flow. So we have a low temperature object on the left, we have a high temperature object on the right. When they come in contact with each other, right, we're going to see a spontaneous flow of thermal energy, right? We're going to see heat, thermal energy flowing from high temp to low temp. And it's going to flow and flow and flow until we reach what's known as thermal equilibrium. Once we have hit thermal equilibrium and these two objects are still in contact, there's still going to be an energy flow from one to the other. But now that the temperatures are equal, that energy flow can actually happen both ways. So now the object on the left can transfer energy to the right. The object on the right can transfer energy to the left because they're at the same temperature. The particles on average are all going to have the same kinetic energy on average. Again, there's still going to be some low energy and some much higher energy, which is why that transfer can now go both ways. But until then, until we reach thermal equilibrium where they're each at the same temperature, we're only going to see that heat flow from high temp to low temp. That's the direction that it's going to go. As our heat transfers, right, so as we're able to get that heat to flow from one place to another, right, that thermal energy moving from one place to another, we have three ways that we can get heat to transfer. We have conduction, convection, and radiation. Now, these are all terms that I'm sure you've all seen before at one point or another, but we'll still go through them anyways because they are important to how we're able to get that thermal energy from one place to another. Conduction is the easy one, right? That's the obvious one. You have to be in contact, right? So this is going to be from collisions between the vibrating particles themselves. And we saw this in that animation. Those particles physically hitting and bouncing off each other, that's going to be some conduction there. The other way, if you look at the diagram in the bottom right, this person holding the pot, their hand is touching that metal handle on the pot, so we're going to get conduction. If you were younger as a child and your parents said, hey, don't touch the stove, it's hot, don't touch the stove, it's hot, and then you touched the stove anyways and you burned your hand through conduction because that thermal energy was able to transfer directly from the surface of the stove to your hand, right? And that is a direct contact that is required here for conduction. Because of this conduction, right, noting that the substance doesn't change location, this can occur solids, liquids, and gases, right? We can get that conduction there. Now convection, right, our next one. This is going to be particle movement, right, that is going to be moving relative to the source of the heat. And because of this, it can be a fluid. And a fluid does not just mean liquid. Fluids are liquids and gases. You've probably seen or heard convection currents under the crust of the earth, right? We get those magma, those convection currents that occur, right, where we get higher temperatures at the bottom because of conduction with the heat source. Because it heats up, it has a lower density, so it rises to the top where it cools off and it sinks, and then it gets to the bottom and it makes contact again. So we get conduction of the magma, and then it moves itself up and down and up and down. The atmosphere actually does this as well, right? As the atmosphere actually gets some convection currents in it as well. So we get any fluids, so liquids and gases can do this. And then radiation is the last one. This is our bombardment of photons. Basically, some sort of electromagnetic energy has to be shined or has to be directed at an object, and that energy is going to be absorbed by the substance, which is then going to cause an increase in the thermal energy of that particular object. Think about the sun shining on the earth, right? That light, all of the radiation from the sun hits the earth. That's a radiation thing. You go outside, you sunburn or you tan, right? And as you burn or tan, that's the result of your body adjusting to that new energy that is hitting it, right? It is absorbing that energy into your skin, and it's actually causing your skin to change color as a result. The other way, if you're sitting at a bonfire, right, and you're sitting close to that fire, you're feeling the radiation coming off of the fire itself. That's what's keeping you warm, not directly touching the fire itself, because that would just be a bad idea. And really what we're going to look at here for thermal conduction, right, is the idea of what's a good and what's a bad conductor. And this is our ability to transfer energy through contact. So if you think about objects that are good conductors versus poor conductors, right? Metals, we typically say are good thermal conductors. When you touch a car door in the summer, it feels really hot. When you touch a car door in the winter, it feels really cold, right? Its temperature is able to change very, very readily. Same thing with, you put a pot of water on the stovetop, and if you touch that metal is going to be hot. You take a baking sheet out of the oven, it's going to be hot, right? That's why you got to use the oven mitts. Now, non-metals typically aren't good conductors. So if you think about like glass, for example, if you touch your car door in the summer and then touch the window glass does not feel as hot. If you take a glass dish out of the oven, same thing. That glass dish doesn't feel like it's as hot, even though it's at the same temperature, right? It's that its ability to maintain its current temperature. So that's what we have here, a little bit of heat, a little bit of temperature, and then our methods of heat transfer. Thanks, folks.